Now that we've used the autosize feature to determine a duty point for our pump, let's explore replacing the autosized pump with an existing pump model and evaluating its actual pump performance in the system. To model the performance of any pump listed in the database, we first need to disable the autosize feature. Let's explore the boosters database to review the information users can add. For a centrifugal pump, entries can include capacity, efficiency, and NPSH curves, as well as operating speed and impeller diameter information. Other types of boosters require different sets of data depending on their specific operation. Returning to our model, once the autosize feature is turned off, we can select a pump model from the database by clicking the three-dot button. In this example, I'll select a pump that meets the system requirements. Once chosen, the pump is integrated into the model with its associated performance curves. With the pump integrated into the model and delivering flow based on the system and capacity curves rather than being constrained by an inflow, we can now reintroduce a flow controller to this leg. To complete the system as a circuit, we'll use a reservoir tank here in place of the known pressure node. The reservoir allows us to specify pressure and a fluid similar to a pressure boundary, but it can also accommodate multiple connections. Next, we'll add return headers to the tank. By multi-selecting the headers, we can set their size to 4 inches. Afterwards, we'll switch to the list view to delete all pressure boundaries, providing connection points for each leg to the header. Finally, let's add heat exchangers to the circuit. FluidFlow supports both shell and tube and plate-type heat exchangers and calculates friction loss using standard relationships, manufacturer-provided data, or a fixed value for each exchanger. For now, we'll leave the heat loss calculation off and revisit heat transfer options in a separate video. Before hitting calculate, let us save our model. Now that the model is set up, we can hit calculate and observe how the pump performs. We can see that the model has converged without significant errors. The results show that the pump is delivering a flow rate higher than the required 50 cubic meters per hour. Using the pump chart, we can verify that the duty point is positioned at a reasonable location on the curve and is relatively close to the pump's best efficiency point, or BEP. It is also worth mentioning that FluidFlow allows us to adjust the pump's speed and apply the affinity laws to generate a new curve. However, the maximum and minimum values for these adjustments should remain within approximately 20% of the original curve data to ensure accuracy. For this example, let's try to decrease the pump speed to 700 RPM and recalculate. The updated model now generates a warning indicating that the booster is affinity law corrected and that the position of valve 18 has exceeded the maximum limit. Looking at the results, we can see the valve opening is at 75.31%, slightly above the 75% limit specified in the warnings and hints dialog. At this point, we can either choose to ignore the warning, given the minimal excess, or make further adjustments to the pump speed to eliminate it entirely. This concludes the Get Started series. We hope it has helped you become familiar with some of the basic features and functionalities of FluidFlow and given you the confidence to begin your modeling and analysis effectively. If you have any questions about modeling or require further technical support, feel free to reach out to us via the addresses shown. Thank you for joining us, and we look forward to supporting your success with FluidFlow.